Hi, and welcome back to our chemistry flipped classroom where we're continuing our conversation about thermodynamics. And today we're going to be introducing a new concept called entropy. So we've talked about enthalpy and we've talked about Hess's law. So we've talked about the release of energy in the form of heat. Now we're going to talk about a different form of energy called entropy. So today we're going to be learning what entropy is, how we can calculate it, and what it tells us about whether or not a reaction is likely to happen. So first we're going to define entropy. So we have a lot of different ways of measuring entropy or defining entropy, but it's really just a measurement of the number of possible states for a system. So it's a way of measuring randomness or chaos. And so we know that nature tends to move towards randomness. This is my children's favorite example for why they shouldn't have to clean their rooms, because entropy always wins and we can just accept that and let the room be messy. As a parent, not so much. So we know that nature moves towards randomness. We also can, when we think about entropy as a measurement of the number of possible states, number of possible locations for all of the different molecules or particles, we know that the entropy increases as we move from solid to liquid to gas, because as our particles move more, entropy increases. As they have more freedom of movement, there are more possible locations for them. And so the higher energy, essentially the state of matter, the higher the entropy is going to be. So solids have the lowest entropy, liquids are higher, gases are higher still. In the same vein, the entropy of solutions is generally higher than the entropy of the components. So by combining a liquid and a solid, we are creating a mixture that has more entropy than either one of them alone. And again, we can think about this as how hard it is to locate one particular particle. So if we think about one particular particle in a liquid, it's kind of hard to keep track of. But once we add in a solution and we have other particles, it becomes even harder to keep track of. More complicated molecules also have higher entropy because they have more potential orientations in space. So entropy is just this measurement of randomness. Now, obviously, we can measure the change in entropy, just like we can measure a change in enthalpy. We also have, just like enthalpy, tables of standard molar entropy. Now, unlike enthalpy, where we can only measure a change, with entropy, we can actually quantify the entropy of a substance. And so when we look at these tables, when we look at the tables of enthalpy, they are tables of standard enthalpy of formation, which is a change. But when we talk about standard molar entropy, that is the entropy of the thing. It is not a change. However, just like enthalpy, we can calculate the entropy of a reaction by subtracting standard entropy of the reactants from standard entropy of the products. If we have a positive delta S, a positive entropy change, that means we have an increase in randomness. Okay, so that means that our products are more disordered than our reactants. So we're going to go through a practice calculation just as we have with enthalpy. So we're going to calculate the delta S for the combustion of methane from standard entropy values. So here we have methane plus oxygen yields carbon dioxide gas and gaseous water. And so our equation is the same. The only difference that you'll notice is that there's not a delta in front of the S in products and reactants. So the change in entropy is equal to the sum of the entropies of the products minus the sum of the entropies of the reactants. And so we're going to go to our table and we're going to look these up, and we can find the standard entropy of methane and oxygen and carbon dioxide and water. Now, here's another important difference. You might remember that the standard enthalpy of formation of any element is always 0. But here you notice that we have a standard entropy for oxygen, and that's because entropy is a measurement of disorder. And so even though it's in its standard state, oxygen has lots of disorder. You notice that that's actually one of the largest numbers in there. The only one that's bigger is the carbon dioxide, and that's because that's a more complex molecule. So at the same temperatures, carbon dioxide has more disorder than oxygen, but both of those gases have more disorder. So we have lots of disorder here.
Pardon the interruption, but this is a reminder that staggered releases should start now so that we can start G-Bell on time at 8:55.
Sorry for the interruption. Okay, so now we're going to plug all of this into our equation that says that delta S is equal to the sum of the entropies of the products minus the sum of the entropies of the reactants. And so we can plug all of that into our equation. You notice that we have the value of carbon dioxide plus 2 times the value of water minus 1 times the value for methane plus 2 times the value for oxygen. And we get that our change in entropy is negative 5.2 joules per mole Kelvin. And so that's how we calculate a change in entropy. We can also make predictions about changes in entropy if we go from having solids or liquids as reactants to having gases as products, then we can expect that the entropy is going to increase. We're going to see a positive delta S. Okay, so we're going to pause here and we'll come back to talk about Gibbs free energy.